let's talk about simple harmonic motion, or SHM for short. This first video is just a brief overview of what this motion is and the equation to describe it. Later we'll talk about how do you get that motion and how it works for certain cases like pendulums and masses on springs. So first thing you need to know about anything with cycles in it is that we have these two quantities. We've already done these at some point in the past, but it's been a while. Let's use this one. Okay, so we're going to be talking about a motion that repeats itself over and over and over again, like a wave. So the first thing we need to know is something called frequency. Frequency. Wow, I'm sloppy today. Okay, frequency F. Okay, looks like the symbol for friction. Sorry. This is the number of oscillations in each second. Okay, number of cycles that happen in each second. So basically the number of cycles per unit of time. The unit is called a hertz. Oh, I'm gonna color code these things. Here we go. Okay, the standard international unit is called a hertz, or Hz for short, and 1 hertz is basically 1 cycle per second. So what you end up with is 1 over seconds. Or sometimes we'll write that like this. Okay? So these are the same things. Another quantity we're going to be talking about a lot is called period. Now we already talked about period when we were talking about the orbits of planets. So period is the time for one complete oscillation or cycle. Okay? So period, which is T, is the time for one complete oscillation or cycle. Basically, it's the opposite of this, the time for one cycle. So to get it, you do the time it takes divided by how many cycles you got, how many cycles you did. Okay? Notice these are exactly reciprocals of each other. So something you can do is relate these to each other. By the way, this is in seconds. I guess I should write that down. I might as well be consistent. SI unit is 1 second. There's nothing really to say about that. Anyway, I can relate these to each other because they're reciprocals of each other. So I can say that the frequency is the reciprocal of period, and I can also say that period is the reciprocal of frequency. Okie dokie. These apply for any kind of periodic motion, that is, a motion that repeats itself at regular intervals. But simple harmonic motion is something special. This is motion that repeats itself in a particular way, that is, the particle, if a particle is moving, it's moving in relation to the origin in a sine function. Basically, I've got an animation of this. Here we go. It is motion where it's like, woo, stop, back and forth, and back and forth, and back and forth. And if we were to graph this object's displacement from the origin, here it's graphed in time, you would get this, which is beautiful sine function. Okay? Whenever you can graph something's motion as a sine function, we call it simple harmonic motion. And when you can do that, there's all kinds of interesting math that you can do. So the basic equation for simple harmonic motion, and I'm going to go back to full screen here. The basic equation looks like this. I'm going to write this kind of big, and we have to point out what each thing does. So we say the displacement as a function of time, which I've already messed up. Okay, the displacement as a function of time is going to be equal to this cosine omega t plus phi. Okay, where this is the amplitude. It's the maximum displacement from equilibrium. Amplitude. Okay? Basically, this is as big as you can get. And I know that because whatever I do, whatever the heck this stuff is, the most I can get from a cosine is 1. So basically we're saying that the most I can get times xm is 1 times xm. So that means that the displacement, the biggest displacement I can get is xm. Okay, so amplitude is the biggest displacement I can get. Then, well, you know what cosine is, hopefully. Omega here, omega, that is the angular frequency. We'll talk about that in a second. Angular frequency. Okay. And this thing over here is a phi, or phi. I actually don't know how it's said. I've heard it both ways many times. This is called your phase constant, or sometimes your phase angle. I prefer phase angle myself. Phase constant, sorry. I don't even remember. Phase constant or phase angle. By the way, I will often draw a phi angula. What did I angle? What? That was weird. I will often draw a phi like this. Okay, it's just a little faster. Those are the same thing. This is like a sloppy shorthand way of saying it or something. I also think it looks prettier. I don't know. Whoosh. Anyway, okay. And this whole thing that's inside the argument for cosine, this whole thing is called the phase. Like this section is called the phase. Phase. Alrighty. Okay, we're going to talk more about this in a second, but let's look at this angular frequency thing. To interpret what's going on here, and okay, first thing we're gonna pretend the phase angle is 0 just to make things a little easier. So I'm just gonna ignore this thing over here. Think about that motion again. Let me go. Let's see, what color do we want to use? Let's use this. I'm gonna go back to that picture. So I know that the definition of period, for instance, is the time it takes for one cycle. So let's say I start the clock right here at the top. Boom. Okay. Boom. Right there. I know the time for one cycle is the time it takes to go from here to here. Basically, I am back where I started if I allow a time of period t to pass. So I know that if I use this equation over here, I know that I get the same number for that equation where the time is just t. Okay, so omega t. I should get the same number as if I do this equation for a time of, and I'm going to erase my little hand-drawn angles because I'm running out of room. Yes, Charlie, I know you're weird. Okay. Sorry, my cat is going nuts. He's been attacking the carpet for some reason. Anyway, I should get the same value, and so I can set it equal if the time that I'm using is not just t, but t plus period. Okay? Because this is back at the same place. Remember, this is giving you the place where you are at a time t later. Okie dokie. Okie dokie. Something else we know is that cosine and sine and all these trig functions, they repeat themselves when you've gone 2 pi. Like basically when you get to 2 pi, the argument or phase here, when this, you add 2 pi to it, cosine just doesn't change. So it's like right here, I get the same function here, that's 2 pi, and then if I add 2 pi to it, I get the same thing over and over and over again. Basically, whenever you add 2 pi to the argument inside of a trigonometric function, you just get the same answer over and over and over again. So, that means that the arguments are basically the same if I say this. It's saying basically this argument, this argument, and this argument plus 2 pi is basically this argument. So I can say this argument plus 2 pi will give me the same cosine function. Since these are the same, I have to get the same cosine function as omega t, omega times t plus period. There we go. Alrighty. If I do some simplification of this equation, I end up with omega times period equals 2 pi. All I did there is distribute this, combine like terms, move some things around. You can figure that out your guys' selves. Yeah, you can figure that out. Okay, anyways, so I get this. So if I rearrange that, what I'm really getting is that omega thing that's in there. Omega is 2 pi over the period. Okay? Or, since period and frequency are reciprocals of each other, also angular frequency is 2 pi times normal frequency. Okay? Which kind of makes sense. Angular stuff often has 2 pi in it, so if I'm calling it angular frequency, it's probably just frequency with some 2 pi in it. Okay, this is important. Write this down, all of this. You're going to be using both. This can be very, very useful because it means that if you are given an equation for simple harmonic motion, you can just yank out the frequency of it by looking at what's right here in the argument for the cosine. So let's do a little example. Let's say that I told you, this is kind of distracting, isn't it? Okay. Okay, yeah. I'm going to rewrite this. So in general, position with respect to time is your maximum displacement times the cosine of angular frequency times time plus the phase angle. Okay, let's say that you are told that a certain particle moves about the x-axis with this equation, where its position on the x-axis is given by 3 cosine, 4t plus 3, like that. And you're like, what's the period? What is the period of the particle? And this is the kind of question that gets asked on the AP test all the time. In fact, when you look at your multiple choices, all the multiple choice questions are kind of like that. Well, I know that omega equals 2 pi over t. So, omega equals 2 pi over t. Since this is in this format, I can just yank and say, hey, omega's 4. So 4 equals 2 pi over t, or period. Okay, solve for period. Let's see, multiply by t, divide by 4. I get that t is 2 pi over 4, or pi over 2. That's it. 2 pi over 2 seconds. Now you could put, pi in, but most of the time in physics we actually just leave the pi's. It's weird. Anyway. Next up, we're going to look at what you can do to find the velocity of an object undergoing uniform circle motion, simple harmonic motion.